So yeah, the next one should be highly related to the measurement of the vertical distribution of the aerosol, coming from Carol Wang, Professor Sheng-Hsiang. Please go ahead. Thanks.
Especially for our Indian colleagues. I hope today, it's the first time to meet you here, and I would like to share what I'm study. It's mainly focused on the vertical distribution of atmospheric pollutants based on the UAV measurement, which you probably very interested on what we are doing here in Taiwan. Before that, I would like to give you a very brief background. In Taiwan, the small island, we suffering a very bad air quality in wintertime, especially in the southern Taiwan. As you see in this figure, during the northwesterly flow in the wintertime, the wind flow go blocked by our terrain. Most of our air pollution will be accumulated in the leeward side. So you see the hotspot is right here. So affected by many effects like the flow, terrain, sea breeze, and the wake. So this is kind of why we are very interested on why what the air pollution causes in the southern Taiwan. So in this particular season in winter. So so let me introduce my capacity of my measurement in this field campaign. We have a field campaign last year. We call it CAPAS. This field campaign aligned with NASA Asia AQ field campaign. So it's kind of the same period. So we have several. So it's been a long while. So right now we have a capability to measure all the gases, NO2, TVOC, and also the particle PM2.5, ozone, and all the meteorological parameters. Especially for the ozone, we have instruments using the UV absorption measurement at 254 nanometer reference. We can characterize very accurate ozone concentration in vertical profile. Also, we have several low-cost sensors, NO2 and the TVOC. So those data have been, and also before, also we have a wind speed and the wind duration measurement from the UAV. Those parameters have been validated by other measurements. For example, here I'm showing the blue line is the UAV data. We measure the wind profile from the surface to 2 kilometer high, and this is for different profiles. And the red line is a wind LiDAR data. The wind LiDAR is a hero instrument. It's very expensive in the high accurate instruments. So we locate in the same location, and we retrieve the wind profile very well. You see the pattern is almost similar. So, but the wind LiDAR can provide more details variation of the wind in vertical profile. But overall, the correlation for the wind speed and the wind duration is quite well. So this is for wind, but for our ozone, we do two-step validation. One step is we fly to the high with the surface air quality station. We compare the ozone concentration at the particular high, and we see the variation of it's a two days validation. So from the air quality station is showing red, but the blue line is showing the UAV measured ozone concentration. So they are quite in the very good consistent trend in the diurnal pattern. And during the field campaign, we have a good opportunity to compare with NASA DCA aircraft measurement. It's a NASA aircraft. But it only provides the very high accurate ozone data in a particular high. So for example, in this ILP, we have a 800 meter high DCA measurement to compare with our ozone profile. So we at this location. So looks like all the data looks very agree to each other very well. So we have a lot of confidence on our measurement in this field campaign. So if we combine all the UAV profile during the field campaign, we come out with the diurnal pattern from the 0 local time to 24 local time. So our UAV measure the vertical distribution from surface from 0 to 1 kilometer high. So this is for the ozone, and actually you see the quite different diurnal pattern in the two stations. In this field campaign, we have two UAV stations launching the UAV in the same time. So we have continued data from the coastal side and the inland side. So it's the coastal side, we see the ozone concentration always have a higher value at the higher level. It's around 600 meter high. So this gives us a very good idea. The ozone high ozone concentration not only showing the surface at the room time, but even showing the higher concentration at a higher level from our UAV measurement. And but for the inland light, inland side, we see the ozone concentration at the night time quite the titration effect is quite large. So we see very low ozone concentration during the midnight to early morning. So this is quite different characteristics between the coastal side and the inland side. In addition to the UAV, actually we also developed the balloon sounding, the radio sound. So all the technologies developed in our lab. So we have a balloon with a small balloon, but we carry our local sensor to measure the vertical distribution, including the temperature, relative humidity, pressure, wind, also the PM 2.5. So we can receive the data immediately from the receiver at the ground. So so this is our deployment map. So all the red dots is all the sounding station. In this field campaign, we have 4 sounding station. Is outside the outside of the domain, and the main area we deployed the UAV in the blue triangle, and this is green is green LiDAR. So it's our measurement strategy is we have a sounding every 3 hours, and we can measure the sounding profile up to the 12 kilometer high. But the UAV we launch every 1 hour, and we can measure only up to the 1 kilometer high. Combine the sounding and the UAV, so we can capture the regional very quite well vertical distribution, including the regional to local circulation. So the wind LiDAR is a very high resolution. It's 1 minutes resolution, and the wind LiDAR gives us the vertical profile up to the 6 kilometer high. So let's look at the PM 2.5 profile from the sounding. And as I told you, we have 4 stations from the sounding. So we can characterize there's 3 stations in the west coast and the 1 station in the eastern coast. And the west coast, they have a very similar pattern like this, but the east coast have a different story. But today I'm going to focus on more western coast of Taiwan. So as you see from the 3 sites of the west coast, they have a very shallow below the 5.5 kilometer high. There is a peak value, is a high concentration of PM 2.5. All the 3 sites all see this near surface high concentration. But actually, you see about the 2 kilometer high, you see the other peak. Okay, so this other peak is due to the biomass burning transport from Indochina, including from the Myanmar, Thailand, all the long-range transport can also all the way transport to Taiwan. And between is a transition, or we call the residual layer. So basically in the Gaoping, the CAPEX, during the field campaign, we can characterize there's the 3 layers distribution of aerosols in this domain. So, but we do some calculation. So there is we can concentration percentage. If you are interested in the integration PM 2.5 concentration, which is AOD, so you can say in the vertical column of aerosol is counting by the surface below the 5 kilometer high, 500 meter high is about 30%, and between the 500 to 2,000 meter is about 40%, but above the 2 kilometer is about the other 30%. So this is the total count in 100. So we have very good instruments, wind lidar. So this wind lidar provides a very detailed vertical wind profile structure. So the slide I want to show you only the mode of wind direction during the polluted day, during the field campaign. Okay, so you can imagine all the polluted days during the field campaign, they have this kind of most wind characteristics. So in the near surface, we can say the 500 meter is a distinguished, the very different character during the nighttime. So during the nighttime, you see the near surface below the 500 meter is a northeasterly wind, but above is a southerly wind. So this is a quite unique characteristics. So this south wind and the north wind can contribute, a very strong inversion layer in vertical. And also you can see the 24 hours diurnal pattern. You see the northeast wind and the northwesterly wind. The northwesterly wind is due to the sea breeze during the daytime. Okay, so we will cover that from the other data set. So this is the mode of a wind direction. So we already can see the average characteristics of the wind field in this area. And so right now I read up one conceptual model, but give you more sense, more idea about what's the three layers air pollution transport in this area. So we have a northeast wind in the surface. We have a 500 meter high south wind, and the upper level we have westerly wind. So this you can just remember this three-dimensional transport diagram. So during the field campaign, I mean the last year we have a 2-month field campaign. So then we have identified 4 IOP, but I'm not be able to go through all the IOP, but I just want to highlight there is a very complicated distribution. So the figure showing you here is the LiDAR data. We have a micropulse LiDAR at this area. I also in charge of the micropulse LiDAR, and also we have an air quality station. So we have a sun photometer measure the AOD. So the pattern, I probably all the Indian scientists all know this pattern. So we have a different aerosol source, like including some dust from Asia. Okay. So at the upper level we have a biomass burning, like here we have a biomass burning aerosol. So, but I'm not only looking at the IOP1 because IOP1 is the simple case in this during this 4 IOPs. But even it's very simple, but it's still complicated. So this is IOP1 from the February 14 to 16. We have a wind LiDAR data. So you see the strongly southerly wind and the more weak northerly wind, and also the other is northeasterly wind with a very stronger, higher wind speed right here. So you can from the figure you can see some diurnal pattern. Okay, day to day. Okay, so but I want to combine. I color coded with warm color from the south, the blue color from the north. So you can see from the north, the wind from the north bring more air pollution. The big one is the PM2.5 concentration. So you see the PM2.5 concentration is higher during the blue arrow and lower during the red arrows. So that means, give key findings. The near surface northwesterly wind usually carries polluted air, especially during the frontal passage. So this is a frontal passage area at the time. Then the middle layer is mainly due to the southerly wind, and then tends to be higher wind speed and blow cleaner air. Okay. So I also can produce for other IOPs, but as you see, there is a very complicated. So IOP1 have a lower PM2.5 concentration. For the IOP4, we have a very high PM2.5 concentration. And there is several like a cyclonic or cyclones circulation in the vertical structure. So I would like to say this is very complicated in this area. In the different IOP have different wind characteristics. But all of the IOP, they have tends to have nighttime inversion. So here we using the UAV to measure the temperature and the relative humidity, and we can use the UAV identify the inversion layer. So we see that all the inversion layer also always showing after the sunset from the 19 to early morning at 4 o'clock in the morning. So during the nighttime, we have inversion layer. This area we see the inversion layer. During in the inversion layer, we have also see the high PM2.5 concentration. So in other words, that means at night actually we have a higher pollution. It's the most polluted time period at night, not in the morning. Okay, but so this other figure showing you the wind, the sea breeze wind. So we have a very we have many weather station over this area. So each arrow showing the one weather station, and then we plot all the wind direction and the wind speed in the meantime. Okay, so in the morning, afternoon at 2 o'clock. So we see during the in the afternoon there is a sea breeze coming to the inland. So I just want to show you this is more complicated. I'm sorry. So there's the vortex. So create the complicate the pollution event. So that is all what I want to mention. This is a very complicated area, and we see the circulation and the air pollution events. Okay, thank you so much. I'm sorry to take more time than what I expect. Thank you.
Okay, thank you very much for your valuable measurement, Professor Wang. You suppose you should be issue a Richmond. Okay, equipped with a lot of instrument. So thank you again.